Hey, today we're going to be talking about binary, and I've got three big things I want to get across. The first is something about the history of human information recording and why binary is such an incredible system and why we now use it for everything. The second is about how we can represent numbers using binary and how we can use numbers to represent binary. We're going to be talking about a few different systems, including decimal, hexadecimal, octal, and binary numbers themselves. We're then going to talk a bit about characters and see character data come through as well using ASCII. And the final thing is going to be a project where you can build a command line tool to take a string and output it using all these various different forms so you can see what they look like and satisfy whatever your curiosity is about the way these things are represented. Now we're going to start off with the history part, and for that I'm going to take you back 2,000 years and also into a very cave-like room that I found myself in to talk about
the Rosetta Stone. Now the Rosetta Stone, which I'm going to show you up here, is a stone that they found made by the ancient Egyptians, and it contains on it 3 inscriptions, and they actually all say the same thing, but they say it in different ways. So the last inscription, the bottom one, is in ancient Greek. The top one is in ancient Egyptian hieroglyphs, you know, fish, eye, that sort of thing. The middle one is in something called demotic, which is quite interesting because demotic and hieroglyphs actually refer to the same language. So if you had if you were in ancient Egypt and you had somebody read out the Rosetta Stone to you and they were reading the hieroglyphs and the demotic script, they would be reading the same message, not just the same meaning in different languages, but actually you would hear the same sounds, more or less. There are a few slight differences. So an interesting question is, why bother having 2 scripts for the same language? And the answer is that hieroglyphs were originally designed is the wrong word, but they were supposed to be carved into stone. In fact, that's what that word literally means, holy carving. And when you're carving things into stone, it's typically because it's something pretty important, possibly something holy or something, in any case, that is a big deal that you want people to pay attention to. So you don't do it like an awful lot. Now, demotic was developed later in a context where more people had learned to use written language and they needed to use it for everyday things like documents and commerce and stuff like that. And you don't really want to wait around for a stone carver to do your messages just for, selling a loaf of bread or whatever it is. So what they did is they developed a new script that was particularly well suited for brush strokes on papyrus. I think that's the right pronunciation, but a kind of paper essentially. And so the script is organized around that sort of thing. It's related to the hieroglyphs, but you can almost imagine it as a cursive handwriting version of hieroglyphs. So they had 2 different ways at this point in history of encoding the same language into a set of written symbols in the physical world. And you can trace the project of human history of encoding information all the way through from that point to where we are now. So roughly 500 years after the Rosetta Stone was written, somebody in China developed block printing, where you would carve messages into a physical piece of material and then you print it on whatever you wanted to print it on, seals and that sort of thing.
Okay, so wild thing, I was finding this image. Apparently it's the world's oldest known advert, and it's like 1,000 years old, which is cool by itself. But the thing that's really wild is apparently if you speak Chinese, if you understand Chinese written language, which I don't, you can still read it today. Like, I always forget that. Like, the same symbols were in use back then as now. Like, that's a real encoding system. We will get back to computers, honestly, but you got to admire that. If you can understand it, let me know in the comments what you're getting from it.
And then over the next 100 years after that, people became interested in trying to make individual blocks for individual characters that you could combine in different combinations for different documents, which resulted in movable type, which is what they used for newspapers and stuff like that. And then you have typewriters and all that sort of stuff. And that affected the script that was used as well. So whereas at a time in the past, cursive handwriting would have been the most effective way to write fluid, swiftly written letters, Now we're dealing mostly with individual printed characters in a big sequence.
I really wish I was back in that cave-like room now, because it is super hot today, as you can probably tell. Now, the reason I've gone all the way back in time to talk to you about the history of information storage is because I want to impress on you, it's actually a pretty big deal that we've spent the last 100 years moving all human knowledge into this one coding system. And in many ways, it's not a very good information coding system. It has just 2 symbols, which means it takes a long time to say anything, but it does have 2 major advantages. The first is having only 2 symbols makes it very easy to encode in a variety of different forms very reliably. And the second is that we can use binary to store many different kinds of things. It can be represented in many different ways, and it has many different representations. We can use these 2 symbols, 1 and 0, to represent essentially any information, text, video, photo, whatever it is. So me from the editing room to bring in a sketchy diagram here. What I want to emphasize here is, when we're talking about binary code, we've got the raw data, which is here represented as a bunch of random binary I generated. And the cool thing about binary, which is special about it compared to nearly all other information recording systems we've generated in human history, is that because it's so basic and fundamental, it's only got 2 symbols. The thing that's special about it is you have a process of encoding and decoding, which through computers can be very fast. And you can have text encoded in the same coding system as images, sounds, programs, video, 3D, all that sort of stuff. So what makes binary special is our ability to write programs which take the very inefficient yet very flexible system of binary code and to translate it into other things that we care about, like text, even semantics in AI. You get the picture. So that's really what's the cool thing about binary, that it can be simultaneously extremely simple, and with the power of computers can be also used to become extremely expressive through this encoding and decoding system. And what you'll see for the rest of this video is a variety of very simple encoders and decoders, and you can possibly even say all programs really are about the process of encoding and decoding binary data from one form to another. Although that again is a bit philosophical. All right, back to the video. So when you're working with binary, I want you to appreciate how cool it is that we've managed to find a system that can encode any information we've come across with just 2 symbols. In fact, the person who is credited with sort of discovering binary, Gottfried Leibniz, he felt it was so magnificent as to be divine, which I find it hard not to be moved by, the idea that we can represent anything with combinations of just 2 symbols, 0 and 1, or on and off, or present and absent. It really is a remarkable thing to be living in a universe where that's possible. All right, that's enough about history and philosophy and the rest of it. We're going to get down to code, which means I get to sit down. Now to explore binary data, I've got us a little program here, just one function. It declares an array of 10 bytes. So each item in this array is going to be 1 byte long. That's why we're using the char data type, which is just 8 bits long, 1 byte. We then loop over the elements using a for loop, and we print out their index and the value. So here we've got all zeros. Now, curious to note, if we don't initialize this array, we get junk data here. So it's kind of an interesting quirk of C that you can access the memory that used to be in this place before it was assigned. But we don't want that. Now the first thing I'm going to do is set the first item in the list to a binary value, which is 1 byte. 8 needs to be 8. And I'll set that to a 1, need my semicolon. Great. So you can see I can now change it between a 0 and a 1. I've chosen 8 digits here because in all modern computing, it takes 8 binary digits or bits to make 1 byte. A binary digit is a value 0 or 1. So here you're seeing really what the the byte really looks like. If we want to take this up by 1, then we can do it like this. You can see it change. The reason this works is because you may be actually familiar. If I make this a little bit easier to see, I'll put a decimal number here. So I'll put 72 here. You can see that. Now, if you look at this 72, you can tell that it's composed of, you can look at it as composed of two numbers, 2 ones and 7 tens. That's the idea of place value. So this here is the tens place and this here is the ones place. It's the same in binary, but binary goes up not in tens, but in powers of 2. So this is the ones place, this is the twos place, this is the fours place, the eights place, 16s, 32s, 64s, and 128s place. So if we want to convert 72 into binary and represent that, we just need to work out what combinations of powers of 2, of which you can only have 1 or 0, makes up 72. So one way we could convert to binary, of course, is just to try to guess which powers of 2 will make up 72. We'll do a bit of trial and error. There we go. So that's one way to do it. Not very reliable though. So there is another way, which is you successively divide by 2 and take the remainder. Whenever I do this, I make a mistake, so I'm going to use the calculator this time. 72 over 2 is 36, remainder 0. 36 over 2 is 18, remainder 0. 18 over 2 is 9, remainder 0. Now this is going to be 4, remainder 1. Now for this, we just take the 4 and divide by 2 to get 2, remainder 0, and then 2 over 2. 2 over 2 is 1, remainder 0, and then 1 over 2 is 0, remainder 1. I could do those last few, it turns out, by hand. Now, if we take the remainders from the most significant bit at the end through to the least at the top, then we've got 1, 0, 0, 1, 0, 0, 0. And then that's what we get, 72. Let me just prove that it's really working. 72. So that's the approach for converting from decimal to binary by hand. Divide by 2 successfully and take the remainders. I'm going to insert a little bit here about why this works. Okay, so when I was doing the binary division thing to convert from decimal to binary, I got curious, like, why does division with remainder work like that? And I recorded something about it, and then it wasn't very good. So I'm recording it again with a amazingly better recording, hopefully, than the first time. Now, this is the intuition I developed. It may or may not be mathematically sound, but hopefully it gives you a sense of why this works. So let's say we got the number 13 in decimal, and we happen to know this is represented as 1101 in binary. And what I'm going to do is I'm going to talk you through how you can algebraically work out that this is the case. So the key for it is, first, let's say we already know this. We'll kind of put in some unknowns soon. We know that what this binary number means is that 13 in decimal is equal to 1, that's the first bit here, multiplied by 2 to the power 3, which is the place value, 1 times 2 to the 2 squared, which is the place value again, etc., etc. So we've got the 4 bits here multiplied by their place value. We can also expand this out, so we've got 1 by 8, 4, 2, and 1. Now, let's say we don't know what the value of these bits is. So in a typical case where we were trying to convert 13 out into binary, we can say, we can express this with this equation. So 13 is equal to 8a plus 4b plus 2c plus 1d. Now, the thing that makes this, it's not obviously solvable with at least any of the algebraic rules I know about, but we can say that since 13 is odd, there is no way let's say that, 13 is odd and A, B, C, and D must be 1 or 0. There is no way to create 13 out of 8 times something plus 4 times something plus 2 times something, because it would have to be an even number, because all those numbers are even, and an even number times an odd number is an even number, I believe. So we must have this final term which is the only way to create an odd number. This final term D has to be 1, because it's the only way we can get an odd number is by putting 1 in this D term. Otherwise it would have to be even, and it's odd, so we know that D has to be 1. We can then take D out because we know what D is, so we can subtract 1D from both sides. Then we divide everything by 2. So that gives us 12 over 2 is 6, then 8 over 2 equals 4, etc., etc. So we get 6 equals 4a plus 2b plus 1c. And we have the same situation again where we can work out that since 6 is an even number, then then c has to be 0. I think that's right. So I lose my confidence here, so I'm voiceovering again. Yeah, obviously it could only be 0 because if there was a 1 anywhere in the combination of 4 and 2, if you added a 4 to any combination of a 1, if you added a 1 to any combination of 4 and 2, it's going to be odd. So here's me looking like really smart and sophisticated for another few seconds. I think that's right. Anyway, I'm sure I'll hear about it if it's not. So then we now know as a result C is 0. Then we can subtract C from both sides. C is 0, so you don't have to subtract anything from the left hand side. Divide by 2 again, and you've got a similar situation as before where you can say what B is, and then we know that 1 is A as a result of the usual rigmarole. So this is how I gave myself an intuition for why this system works. I don't know how mathematically sound it is, but I thought I would share it because I thought it was an interesting way of putting it and solving the mystery for me, at least. Back to the rest of the video. So this is how we represent unsigned, that is no minus sign, integers using binary in a single byte. Now this way of representing numbers has a few interesting characteristics in binary. So one thing that's, let me actually open up a new one here. One thing that's a bit interesting about it is that it's bounded. So if we have everything be 1, we get 255. And if we have everything be 0, then we have 0. So this can only represent the numbers from 0 to 255. If you try and increment this by 1 in most programming languages, you're going to get you're going to get a warning, and then you're also going to get 0. So if we take this up by 2, you're going to see that it wraps around. So if you ever experience this wrapping around behavior in integers, with very large integers, that'll be why. Another interesting facet of this encoding system is that much like with decimal, if you want to multiply by 10, you can add a 0 to the end. And if you want to divide by 10, you can take a 0 off the end. With binary, it's similar, but it's with 2's instead of 10's. So if we want to multiply 72 by 2, we can add a 0 to the end. And if we want to divide by 2, we can take a 0 off the end, which is handy to know. Sometimes this is called shifting. So if we were to shift all of these bits to the left, we get something like this, which is the same as multiplying by 2. And if we want to shift these things to the right, we add one to the start and take one off the end, and we get halving. In numbers anyway. In other, if we're looking at different kinds of data, that will do different kinds of things. And if you want a nice straightforward way to convert numbers to binary without having to go through all of this rigmarole, then Python has you covered. This 0b on the start, by the way, is the prefix that indicates it's a binary number rather than any other sort of number. Now, one thing you'll notice about binary as a number system is it's not very space efficient. You have to have 8 whole digits for just the number 72. And you can imagine that this gets pretty arduous to look at and certainly arduous to code in. Decimal, though, is not super easy to work with either, because the same number of bits in binary can get you different numbers of digits in decimal, because decimal 10 is not a power of 2. So it's kind of awkward to work with and not super easy to read. So when we're working with binary data, we tend to use a different numerical system called hex, which is base 16. So that means it's got 16 different digits, which range from 0, 1, 2, 3, you know, the classics. And then we switch to A, B, C, D, E, and F. So we've got 16 digits here. We can use Python to convert from decimal to hex as well. So if we stick in our next number, 101, it gives us out a representation of that number using hex, which I can now put in here. So this 0x here is the specifier that indicates this is a hex number rather than, say, a decimal number. Now if we run this, we can see the 101 comes out over here in decimal. Now the thing that's handy about hex is 16 is a power of 2, so we can now just break down any binary data into groups of 4, and each one of these groups of 4 is going to be a hex digit. So this would be easy to see if I write out my hex in my display, which is, I think, with the X code. Now, if we convert this to binary, so now if we break this up into groups of 4 here, so I can show you this. This is the code for 5, and this is the code for 6. So each group is just 1 digit. And if I were to say swap these over, we get 56 rather than 65. So hex is quite easy to work with when it comes to thinking about the binary representation. They're as close as they can be, but actually hex is even more space efficient and regular than decimal. So it tends to be when you're working with binary data, you're usually looking at hex rather than any other system. Let's shift this back to what it was. Moving on, we can of course add things in decimal as well, and see these come out in both decimal and hex. And there's one more system I want to show you as well, which is octal. Now you probably won't come across octal too much. Octal is base 8, so it uses the figures 0 through 7 and goes up in powers of 8. So there's a handy utility for it in Python as well. So if I put in 108 here, I get this representation out, and you can see it's got the 0, 0 specifier here. Unfortunately, C does not support that specifier. What's the octal specifier for C? It's just an initial 0. Very bad choice, I think, because you could quite easily put a 0 on the front and think you're working in decimal, but you're not. It's actually the same in JavaScript, which is unfortunate, but that's how it is. So you don't see octal much in use anymore. It is sometimes around, but it was more of a historical thing these days, and in particular in networking, it becomes a bit more relevant. It also is in use in Linux file permissions. So the let's say 755 or 644, those are octal numbers because it's only 3 bits involved: read, write, and execute, which is kind of cool, I suppose. Now the last type of data we're going to look at is characters. And characters, well, we can enter one with a string just like this. Let's say F. And you can see that these can also be interpreted as numbers. So the letter capital F is represented by the decimal number 70, or it's represented by a binary string which can also be interpreted as a number in decimal, which is 70, or 46 in hex. And there's a system called, the short answer is there's a system called ASCII, which assigns individual characters numbers and then bit patterns by consequence. So this system assigns the letter A the number 65, B 66, etc. There is a more modern system which is used, but we're not going to touch on that today. We're just going to talk about ASCII. So one of the neat things about ASCII is if we, let's say we get the number 66 and we can express it as binary, and then we put it in here, and then we express this as a character. So you see this is B here. So this number here represents the letter B. This bit here, which is the 6th bit, is the case bit, essentially. So if you have a letter, you can change this bit and you'll end up with either the lower or uppercase version. So if we increase this and get a, I don't know, the letter F, then we can flip this bit and we get a capital F, we flip it again, we get a lowercase f. So just like with numbers, binary gives us certain characteristics, so we can shift bits to the left or right to multiply by 2. Also the systems which encode things in binary like ASCII or other systems, they also have characteristics in the binary domain which we can use. And a really good encoding system will have a bunch of these, which is allows us to play around with it and see efficient ways of doing things. Now, if you're dealing with a real language, then this is really not going to work for you, and you're going to have all kinds of trouble with capitalization. If you just use this approach, you'd need to use something much more complicated, because capitalization is its own really complicated world of arbitrary human rules. But it's interesting to know that at least within the Roman alphabet, you've got a few interesting things. So a little extra thing I discovered in the editing process is if you load up the ASCII spec, not only do you know how to spell it, ASCII, in case you're wondering, you also note that it uses characters that are not in ASCII as part of the document itself. It shows you how limiting ASCII is, or at least not in the original ASCII. It also contains this really cool table, which I've not seen as clearly put anywhere, where you can see the way that these 2-bit strings, so it's actually, original ASCII is actually a 7-bit code rather than an 8-bit code, but we just put a 0 on the start. So if we're looking at the lowercase o here, we can read that it's 6 and then 15, or 6f in hex, or in binary it's 110 1111, which is kind of cool. And so you can then see how the case bit also applies here between columns 4 and 6 and 5 and 7. So you get capital O, lowercase o, capital N, lowercase n, etc. So pretty cool, I thought, and definitely worth showing off. I'll put the link to it in the description should you be interested in saving this table for yourself, because I know I will be. So now let's have this be the O, which is our 111, and you can see that the characters here represent the sequence hello. So hello to you too. Now we've already seen how to print numbers out using printf, which is essentially print formatted. It's not purely in C, but it's a peculiar to C function, and it has these little codes which print things out in different formats because, well, it's just the way they did it. They're a little arcane, but they're also kind of cool when you get to know them. So you can see this little code here will print out an unsigned integer, so a number without a minus or plus sign, and it'll space it out with 3 spaces. I could also do this and get them 0 padded as well, which is useful to know. The X% sign will get you the hex version, which we can also pad with spaces like this, and the C will get us the character. There's also a symbol for octal as well, which I think we can see here. If I get this right, I have to put in the bytes a number of times because we're printing it out a number of times. Yeah, so we got octal here, which we can pad with 3 spaces. And I think I'm going to space these out a little more as well. And I'm going to speed this up, but I'm going to also give us a little header as well. So now we have some nice headers as well. You may be interested in what this all looks like in binary, and we can print it out in binary, but it takes a little bit more work because C does not have a format specifier which will print out binary. Now, we don't have to go through the whole division by 2 thing because our numbers are already represented in binary, so we just need to work out how to display that as a binary string of, well, as a string of the characters in ASCII 0 and 1. So I'm going to write that code and then I'm going to explain to you how it works. Okay, and after a bit of muddling around aligning things, here we go. So now we can see each of these characters printed out in binary. Now to explain to you how this code works, I'm going to take this byte here and we're going to work through it. Now the way to think about this is we want to progressively get the value of each bit and then print that out as a single bit. And then through doing this, we'll be able to build up our whole byte. So we've already gone through this and we want to get the value of this bit here, which I'll just highlight like this. And that's going to be bit 4, or 0, 1, 2, 3. Let's call it 3. To do this, we want to shift this byte right by 3 bits. So you see how we now have this bit in the least valuable position, the value for 1. This doesn't really help us immediately because we've still got this bit here. So if we take the value of this byte, it's going to be 1 plus 1, 2, 4, 8. So it's going to be 9. There's no 9 in binary, so that's not going to work. But we can transform this again using an operation called bitwise AND, which I'm going to indicate here. And we're going to do a bitwise AND between this number, which we got after shifting, and this number, which we've given it just straight out. What bitwise AND is going to do is it's going to go through each bit in the input values, and if both of them are 1, it's going to set that bit to a 1. And if that's not the case, if either of them are 0 or both of them are 0, it's going to set that bit to 0. So what we end up with is, okay, so this is 1 and 0, so it's 0. These are both 1, so we get 1 at the end. So we now know, as a result of these 2 operations, that the third bit along here, the bit that represents the 1, 2, 4, 8, the 8 column, is 1. So we go through each bit, we shift to the right by its number of places, we use bitwise AND to get the final bit only, and then we print that out. And by starting at this one and moving along, we get each one in turn and we can print it out. So a nice example of how to use shifting and bitwise AND in a reasonably realistic operation. Now the final thing I'm going to show you is how we print this all as a string. And it's fairly straightforward. Instead of using the C character to print a single character, we use the S specifier, and we just put in the whole thing, whole bytes, and we get hello out the end. Now there is a little quirk with strings in C, which is that they have to end in a null byte. So the string continues until there's a null byte in it. Here we can see there's actually 10 items in this array, but if we put some specifiers around it, we can see it only prints the first 5 values, because straight after that there's a null byte. Now, it would be interesting to see what happens if we just have 5 spaces in the array. And of course, we'll need to then change this to 5 as well. You'll see that we start to get junk data on the end. And this causes a lot of problems, and it can sometimes be related to the cause of security issues as well. So we always need to make sure with a C string that we're ending it, because you wouldn't really usually specify a C string like this, but we're ending it with a null byte. It doesn't need to be binary, it could just be, in fact, let me open this up so you can see this. It doesn't need to be binary, it could be anything, it could be hex, it could be just a decimal number. It's all the same bits in the end, and you can quote me on that. So what we've looked at here is setting some binary data using binary literals, hex literals, of course decimal literals, octal literals, character literals, and then we've also looked at displaying them using printf, the unsigned integer, the unsigned integer again, the hex number, the octal number, and then we've done some work to print out in binary as well, and finally we printed out characters and strings as well. So lots of cool stuff, and getting familiar with this stuff is really useful when it comes to working with binary data and also understanding the fundamentals of how programming in your tools work. A lot of the stuff that we go on to work on will involve this knowledge, so it's good to get familiar with it. With that in mind, I've got some exercises for you, and the exercises include going and doing some of this yourself with some different bytes. So I've given you a list of bytes on the ODES website just in the description below, where you can go and print those out and also add your own data to it. So you'll be writing a program much like this. You can use this as reference, but it might be fun to try doing it from memory as well. And then there's a second exercise where you'll create a tool called stringspect, which is a command line tool where you can put in a string, give it a string as an argument, and then it will show you, much like this, what's making it up, which is a pretty fun thing to be able to see what string. Try putting emojis into it, try putting non-ASCII, that is non sort of Roman alphabet characters into it, and seeing what makes those up. That might be fun, and you can use your tool stringspect to do that. There's also a couple exercises for members as well, for those of you interested in that. All right, the video is concluded. This one was a real tricky one. I'm still getting the hang of a lot of the editing, performance, basically every aspect I'm getting the hang of. Plus the content, I ended up writing down the learning objectives, which I summarized briefly at the start, but there's actually loads of little bits of material in here which I needed to fit in and make sense and organize. So I hope I did that for you. There are exercises on the ODES website. You can find that in the description for you to do. The whole point of ODES, which is, by the way, a project to help people who want to dig deeper into the field they've chosen, software development, software engineering, whatever it is, and find the love in it. This is only going to happen if you also do some of the exercises and actually get some of this stuff practically working in your own hands, so that you can start to take control over the technology that you want to work with. So there are some exercises on the ODES website that you can do. I definitely recommend doing those. And there are also a couple of members-only exercises as well. Thank you for those of you who are paid members. There is a membership subscription, 10 of your preferred / exactly what Stripe chooses for you, dollars, euros, or pounds per month. And you get extra stuff in every episode, but no pressure if that's not for you right now. The videos will be up here for free. So enjoy them. Enjoy this one. Let me know what you think. Let me know what you think of the exercises, and I will see you in less time than this time. So another week, I'm hoping maximum. So in that one, I'm looking for us to spend a bit more time working with binary data in files, so we can start to dig into endianness, which will be important, although possibly slightly annoying. I'll try and make the history somewhat interesting. And then after that, I'm thinking we're going to make a program. So write a program which will produce an executable. And in that process, we'll also need to learn about how instructions work. at a lower level. So that should be really fun. Looking forward to seeing you there, and have fun with the exercises. See you later.